happy. So I'm very happy to present our recent work here. It's actually basically tells how to compute the self-consistent bonds in force vector decay, or namely calculate the quantum corrections to the bonds. So this kind of thing is actually based on my previous work, but this talk is mostly based on the recent work with Gian Alexander and Samasaka. And for other two papers, my collaborators are Juan Cruz, Bjorn Garbage, Peter Millington, and Klaus Tamrit. So this is the outline of this talk. So before I give the talk, actually, so the talk is a bit formalism heavy, and at some point it may be slightly technical. Well, it's kind of, I mean, it's kind of boring in some sense. So if you have any questions, please do interrupt me at any point. I mean, it's better to ask questions during the talk instead of after the talk. And so this is the outline. I will first give a brief introduction to first order phase transitions. I know most of you are very familiar with this, but still just to be complete. And then I will move on to the standard bounds formalism on force vector decay, which is first order phase transitions at 0 temperature. And then I will go to the main part of this talk, where I discuss how to calculate quantum corrections to the bonds, which is also the quantum corrections to the critical bubble, using the 1PI effect action. So I just want to, so yeah. And after the main part of this talk, I will briefly mention some ideas on how to compute the backreactions to the plasma from the nucleated bubble for first order phase transitions at finite temperature. And well, I will introduce 2PI effect action. Okay, so let's start with the introduction. So what is first order phase transitions? Usually we start a scalar field with some potential like this. And then we assume the field initially takes a value at the minima of the, so classically this actually is a stable state. But however, we have quantum fluctuations, and under quantum fluctuations, then this field can tunneling through this barrier and escape at this point. At the finite temperature, we can also have some thermal fluctuations, and in this case, on the thermal fluctuations, the field can be pushed up to the top of this barrier and rolls back. So this is, we have two types of bubble nucleation. So in this picture, actually, it looks like that the field phi is a one-dimensional thing, but it is actually not. It is actually field configuration, and in principle, it is infinite dimensional space. So for example, a point head here is not just the constant field value. It's actually a bubble field configurations. Similarly, the same applies for the sum of phase transitions. You have a critical bubble field configurations at this top. So for the quantum for the bubble nucleation caused by quantum fluctuations, we have the O4 bonds. So we have to move on to the Euclidean space and study some four-dimensional Euclidean field configurations, so soliton field configurations, which is called bonds. As in this case, actually the energy for the scalar field is conserved. So it means that the energy for at this point and the energy at this point, they're the same. So now from this plot, you might think that this point is slightly slower than this point. How can these two states be have the same energy? Well, because as I said, because this point is not a constant field configurations, it is actually a critical field configuration. So critical bubble field configuration, and then you have energy, positive energy from the bubble wall. But for the bubble nucleation at the finite temperature, the energy of the scalar field is not conserved. So in that case, you do have some energy extracted from the plasma, and in this case, one can imagine that there should be some backreactions to the plasma, which may or may not be important. But I will outline very simple ideas on how to calculate these backreaction effects. Now, this is a more simple picture, the so-called symbol picture. And then you just have the energy for the bubble wall. It's usually given by a term proportional to r squared and another term, negative term proportional to r to the cubic, right? So this is actually the bubble, the bubble, critical bubble for first order phase transitions at a finite temperature. And this is critical bubble nucleated at a zero temperature. Now, so why first order phase transitions are interesting? Actually, they are interesting on the theory side and the phenomenology side. On the theory side, actually, there are many questions. For example, is there any real-time picture for phosphate decay or for first order phase transitions? And at this point, actually, some people actually use the so-called Langevin equation to describe the nucleation of bubble. And also, some other guys actually try to use mathematical theory, Picard-Lafayette theory, to calculate the real-time transition amplitude from the force vacuum to a critical bubble. And for also the precision calculation of bubble nucleation at the finite temperature is very challenging. And essentially, there are many papers studying this. Like, I mean, I know, and he has already have done a lot of work on this. And also, another question is that bubble nucleation categorized by black holes, and in that case, there's also a debate how to actually describe this process. The difficulty is that actually for realistic black holes, the vacuum state around the black hole is not the hard Hawking vacuum where we have balanced ingoing radiation and outgoing Hawking radiation. But for realistic black holes, you just have the outgoing radiation. And people say that for the onward vacuum, in the later case, actually you cannot apply the Euclidean bounce formalism. And also, the phosphate decay is a non-perturbative phenomenon. So and actually there's a duality between perturbative sector and the non-perturbative information of a QFT. This means that if you just look at perturbative sector, so you do not look at some set points as instatons, and you have a perturbative series, and if you can gather enough information and you actually sum this series, you do some Borel summation, and then you can actually get the non-perturbative information. So there's a question that how this picture can be used to describe bubble nucleations, maybe to help us to do some calculations. Also, bubble wall dynamics at finite temperature is also a very difficult problem, and many other things. On the finite side, first order phase transitions can produce gravitational waves. They can also could explain baryon genesis or lepton genesis, and also they can actually produce dark matter magnetic field and also provide a mechanism for primordial black hole formation. So all of this makes first order phase transitions an extremely interesting topic. Now, below, I will actually focus on first wave decay. As I said, it's just the first order phase transitions at a zero temperature. And this is described by the standard bounce formalism. Sorry, the standard bounce formalism. The central idea is given by Callan and Coleman in 1977. So you have a first vacuum here. This is a first vacuum state, and this state we know is not stable quantum mechanically. So it must have in some sort have some complex energy. So the ground state of the first vacuum, and the imaginary part of the energy actually gives you the decay rate. Right. Now the thing is that how to calculate the imaginary part. So to that end, one can consider the transition amplitude, Euclidean transition amplitude from the first vacuum to first vacuum, right? And then you can insert a complete basis of energy eigenstates into this transition amplitude, right? And then you can take the infinite time limit. So in that case, all this sum is projected to the ground state. It means that only the ground state survives. So in this case, in this limit, you just get this formula. But on the other hand, this transition amplitude can be calculated by the path integral, right? So you can combine these two relations and you just get the decay rate in terms of the partition function, the path integral. Now, so we know this formula, and then we just compute the partition function, right? So to compute the partition function, we actually use the method of stiff descent. So the first thing is that you need to find some stationary points of the action. And then you do just expand around the stationary point, and then you can do your integral. I mean, this is your partition function, right? And then you have a classic part and the fluctuation part. So in Euclidean space, actually the potential is upside down in your equation motion. And then you have two types of stationary point. The first one is a trivial point, is a trivial setting point. It's just the field stays at the first vacuum forever. Okay. So just to recall that we consider the transition from first vacuum to first vacuum. So this actually serves as a boundary conditions to this equation motion, for the classical equation motion. And the second type of station point is actually so-called bounce. The field can start at minus infinity time and rolls back, and then at some point, let's say we can say take the tau to the imagined time to be 0 and roll back. So this is the relevant solution that can actually describe the time ring. So with this analysis, well, it's just with this analysis, how can I remove this part? Yes. So then you can get the Callan and Coleman formula. So you have the classic part, and also this functional determinant is obtained from the integrating over the fluctuations around the set points. And this have some factor here is actually related to the zero modes in the fluctuations. Okay. Now, so far we just talk about the bonds, and here I would like to just discuss the relation between the bonds and the bubble. So in for first vector decay, for the O4 bonds, you have some bonds like this. Imagine here I just use a two-dimensional space-time, Euclidean space-time. You have some bonds like this. And then actually at the tau equal to 0, this is also like a circle. So it's like a bubble. This actually give you the critical bubble, nucleated critical bubble. For the O3 bonds, which is actually for thermal phase transitions, and then you have the Euclidean time is actually periodic. You have to identify the Euclidean time, and your field configurations is actually tau independent. So at any tau, you get the critical field, critical bubble field configurations. Now the question is that how to compute the quantum corrected bonds or critical bubble, or even further, what if we do not have a bound solutions at the classical level? For example, in the standard model, it's a Higgs instability thing. Actually, we do not have classical bound solutions. Now, there are actually two methods. The first method is that you just replace the classical potential with the effective potential in the Callan and Coleman formula. But this actually causes some double counting problem, because the Callan and Coleman formula actually is obtained by integrating over one loop fluctuations, right? And then the effective potential already contains some one loop effect potentials. So there must be some degrees of freedom have been doubly counted. So in order to solve this, one can actually separate the scales and construct, you first integrate on some small scales, small length scales, and then you get this effective potential. Okay, so this effective potential is not obtained for the full for integrating over all scales, and then in this case you can somehow construct some nucleation effective field theory, and when studying this effective field theory, then you can actually get a similar formula like the Callan and Coleman formula. But this actually a second method. In the second method is that we do not use the effect of potential. We can just use the effect of action, which actually can give you um, the equation motion for the self-consistent bonds over all scales. And then in this talk, I will just focus on the method 2. So is there any question so far? Okay, so everything is clear. Now, now I'm going to discuss the 1PI effect action. So the steps, the procedure is like this. So we first introduce an effective action that gives you self-consistent bounce equation motion. And with this effect action, we can also have some generalized decay rate formula. And then we Taylor expand the one loop effect action about the corresponds. Then well, you can see you have some new quantity, which is functional derivative of the functional determinant. So I will show you later. Then and also the one loop effect action actually is divergent, and so you have to do some regularizations. But for this, actually, people have done already of this. I will show you two formulas for this, the regularized one loop effect action. And with that, we can finally take the functional derivative. As I said, you will have a new quantity to compute the functional derivative. And then with all of this, you can get the one loop self-consistent bonds and also the quantum corrected nucleation rate. Now, let's start with the 1PI effect action. So with the quantum field theory, we just start with the generating functional. So here we introduce a local source. This is kind of more or less a mathematical trick. And then the macroscopic field configuration is actually described by the 1-point function. So this includes the bounds over bounds and the O3 bounds in two cases. So in the end, if there's no external source, in the end, you will take J to be 0. So with the partition function, you just take the round transform and then you get the effect action. So from this definition, you can see that if you take the functional derivative of the effect action with respect to phi, then you get J on the right-hand side, right? So in the absence of the external source, you just take the right-hand side to be 0. So this is the equation motion, quantum equation motion for the bounds. And this is, of course, is general. If you consider real-time dynamics, this can give you the quantum equation motion for the bubble, and it can be used to study, the bubble dynamics. And here you actually can see some self-energy terms which has never been considered in the literature. Now, with the 1PI effect action, the decay rate can be formulated in terms as follows. So actually, there's a quick way to see why the decay rate takes this form. So as we mentioned earlier, actually, the decay rate is related to the imaginary part of the log of the partition function, right? So which is related to the imaginary part of the force vacuum energy. And then if you take J to be 0, then you see that this term vanishes, and then so this is just the log of Z just to give you gamma phi, and this is actually the bounce action, effect action for the bounce. This term is usually can be normalized to be 1. You can always to define your effect action so that you are not concerned with this part. The only difference is that here you have some exponential. This is actually derived from the multi-bounce contributions, where you use dilute incident gas approximation, and then you can see this exponential Asian process. Now, okay, everything's fine. And then we just try to do something, to do some calculation. And we start with one loop effect action, which is you have classical part and you have This part is functional determinant. Well, M is a fluctuation operator, and the M hat is actually the same fluctuation operator evaluated at the first vacuum, the trivial set point. So you take functional derivative of the effect action with respect to phi, you get the equation motion, and then compared to the classical equation motion, you get an additional term, right? Here, I introduced a notation for the ratio of the functional determinant, so D, and which is actually very important because later I will use this D a few times. So it's good to bear this in mind. Well, this equation actually is not easy to solve. And then one simple way is that we can actually expand this one loop bounds around the classical bounds, right? And then just obtain the equation motion for the delta phi, the difference between these two things. So this term actually, by ignoring higher order perturbative terms, you can just evaluate this term at the class bounds. So this gives you an inhomogeneous differential equation, and we can solve it by Green's function method. Also, if you substitute this expansion to the effect action, then finally you get the form of the one loop effect action evaluated as a one loop bounce. So you have the standard classical bounce action, you have the standard one loop functional determinant, but you have a Newton. Okay. And then in order to arrive this, the only quantity you need to calculate is the functional derivative of the functional determinant, the d phi here. So this is a crucial quantity you need to compute in order to get this precision. So if you know this, you can of course get the delta phi, and then everything is known. Everything is clear. Okay, so let's move on. So far we haven't made use of the O4 OD symmetry. So below we have to use this symmetry to make our life simple. So since that for general field configurations, we do not have the expressions for define the ratio of the functional determinant. We already know this from define for very specific cases. For example, for the constant case, then it is just a one loop effect potential, I mean the collection part. And for the OD symmetric configurations, we also have some formulas to be introduced below. So for that reason, we want to actually also apply all the previous derivations for the OD symmetric configurations, and we expect that the quantum corrected bounds is also let's say O4 symmetric. So this is fine. And then you get the equation motion for this one-dimensional field configurations. Well, field configurations in one-dimensional space. So it's just a function of R. It's not a four-dimensional space-time anymore. And then the effect action is the same, but here you just have the one-dimensional integral dr, and everything is just it looks like you work in one-dimensional space. Okay, so as we already mentioned, the d phi is divergent, and we need to do renormalization. Sorry. Now, to compare the d phi, I mean, even this phi is O4 symmetric. The fluctuations the fluctuation is still not O4 symmetric, right? So in this case, when you calculate the functional determinant, you still have to have the four-dimensional operator in your mind.
Could I ask a question?
Sure.
Hi. So I want to understand better. So with this functional determinant, we account for quantum fluctuations about the classical bounds, right? So
Yes.
the classical field configuration. And then the derivative of the determinant is a quantum correction to the equations of motions, right?
Yes.
Okay, I just wanted to make this distinction.
Exactly. Well, yeah, this is a good point because I mean this is how all this procedure differs from the standard one loop Callan and Coleman formula. Yeah, this with this term you can actually get the corrections delta phi. Delta phi is just the difference between the one loop bounds and the classical bounds. Right?
Mm-hmm.
But if you calculate delta phi, then this new contribution, I mean this will make a new contribution to the uh decay rate because the decay rate is actually related to the effect action, this one. So maybe I can show you. You see, this is gamma phi b. It actually gives you the decay rate. You can forget about this term. So this term can be chosen to be 0. So this will directly go to the decay rate. So this means that if you calculate this quantity, you can obtain two things. One, the quantum corrections to the classical bonds, and the associated quantum corrections to the decay rate.
Okay, thanks a lot.
No problem. So this is also, I mean, this part is also quite a standard thing. I mean, so, but just want to review it, and I mean also for the introduction, and then fluctuations are still inhomogeneous, and then when you calculate this, then you have to do some spherical harmonic decomposition with and then this term can be decomposed into a sum over these terms. And then this terms is a functional determinant. You can actually imagine this is dl phi. So there's no subscript L, but this is you have subscript L dl phi. Now this operators is one dimensional. Now, a very efficient and powerful method to calculate this quantity is Gelfand-Yaglu theory. For this one-dimensional differential operators, then it tells us that this quantity in the brackets actually is given by these two quantities, and the psi L hat is actually solutions to these two equations. Basically, you do not need to solve the eigenequations, which is you have to many eigenvalues, so on and so forth. You just need to solve one differential equation, this one, and also one differential equation for this operator, and then evaluate your solution L at infinity, then you get the ratio of the functional determinant. So this is really a very useful method to dramatically simplify your calculation. So I denote this ratio as TL, as everybody does. And then in order to, I mean, instead of solving these two equations, you can, of course, solve DL directly. And then this is the equation motion for TL. Well, W, I didn't introduce W. W basically is the U pi phi minus M squared. The M squared is actually the mass turn around as the force vacuum. Okay. Now solve TL and substitute TL to here, you get a d phi. Very simple. Okay. Now this is not as simple as we thought because this sum is actually divergent, right? And then you have to get rid of this divergence. Well, this is usually as I mean in quantum field theory, but actually in the literature there are two approach to regularize this quantity. This actually the first one I call the WKB method. So sorry, so the divergence actually is comes from, apparently it's come from large L terms, right? This is, look, L is just like a momentum. And then the first one, you actually can get, you first separate your divergent term is large L part. When L is very large, you can solve the equation motion for TL using the WKB method. And then you subtract, this is basically you compute this numerically. And you subtract your WKB analytic solution, then you get a finite part. Well, and then this part can be, this divergent part can be cancelled by the constants. Okay, so this is one way to regularize this quantity. So another way is actually, I call it the interaction picture. So essentially define is a function determinant of these two terms is sum of these two terms, right? Now if W is zero, let's say imagine that W is zero, then this quantity is automatically zero, right? There's no any divergence. So this means that this divergence comes from interactions. If there's no interactions, then there's no divergence. Okay. So people have shown that actually all this divergence in this define is contained in the first two terms in expanding this quantity. So order W2. So in this case, this is the divergent part. And you can actually, this is a regularized quantity. You have a subject one, this divergent part, and this divergent part will be cancelled by, effectively by constants. Or here, if you use the dimensional regularizations, you can just subtract the power. So finally, you get a finite part. Right, so this is two ways why you get two different formulas. The first one is used by Dan and Min, like in 2005, and then they get this very nice formula. So if you are not concerned with quantum correction to the bounds, then you can directly use this formula to calculate the function determinant. So this is really very efficient. Now the second way, as I said, using the interaction picture, you get a slightly more complicated formula. Again, here you have a log and TL, right? These terms are, well, basically from analytic part. For example, you calculate. I didn't look at it very carefully. Probably from you calculate WKB. Sorry, so the TL using WKB method, and then you get some analytic part, which is divergent. So this looks like this is divergent if you do the sum, but this divergence will cancel this divergence in here. So this is why finally you get a final result. Again, here you also, this term solely is divergent in the sum, if you sum all over all L. But again, you have HL2, these terms will cancel the divergent part. Now, 1, 2 actually is obtained from the expansion in W. So that's what I mentioned here. So you have you just expand the W to the one or first two orders. Okay. So this is why you get two terms like this. HL and HL2, 1, 2 actually are satisfied by certain equation motion. Now, this actually is when we try to do all this stuff, actually, we've obtained an unexpected finding. When if you do not take function derivative of this formula define, then everything's fine. Actually, basically in the paper by Dan and Min, they say that the formula match is this BL formula. They compared numerically. But if you take a functional derivative, then we found that this formula gives you a divergent and cutoff dependent result. So somehow we kind of think that the first equation is valid only on shell. I don't have more intuition with that, because I don't really actually follow how to follow didn't look carefully about the WKB regularization, but this is what we found. And I will show you very briefly why this formula gives you a divergent result when taking functional derivative. Okay, now, in this formula, you can just take a function derivative with respect to phi, right? So this is very easy. Some integrals, and then you get some delta term, and then do the integral, and then it just, as usual, there's nothing strange happen. Now you just need to do the functional derivative with TL. This is itself is a function, and also HL2. So I will now take a TL as an example to discuss how to the functional derivative. We start with the equation motion of TL. HL is just the operator I showed you before. Well, I just so write briefly here HL. And then you can take functional derivative of this equation. Right? So you get two terms. The first term is that TL means delta phi. And second term is actually delta HL means delta phi. Right? So this is the operator, and then you can obtain some delta function u phi phi. Well, HL is have potential u phi. So this is why how you get something like this. Then this is looks like an equation of motion for the delta TL delta phi. You can solve it with Green's functions. Okay. So this is GL is Green's functions to this operator HL. Right. So when you solve this equation, this looks at source for this equation, and then you obtain some formula like this, do the integral, and then finally you get delta TL apply phi with delta phi r, you get a GL something like this. But because in the functional determinant, we actually are interested in delta TL infinity. This is what the Gelfand and Yaglu theory tells us. You're just interested in the solution at infinity, and then you take apply to be infinity. So this is the central formula we obtain. Well, it's actually quite straightforward. So with this formula in mind, then you can actually calculate the functional derivative of the functional determinant. Is there any question? So at this point, no. The same procedure can be applied for calculating the functional derivative of HL1, HL2, and again you have to calculate a bunch of Green's functions. Now, let us go back to the dumb mean formula. So what's wrong with this formula? So you can see that if you take the function determinant of TL, as I said, then you get some and take and you just look at the R to infinity. Okay, just look at one point. Then here you get a coincident Green's functions. Yeah, and the Green's functions can be solved analytically. Well, not analytically. It has a analytic expression at least. And F1 and 2 are two basis solutions to the same operator, differential operator. And then you can see that actually the constant Green's functions is actually vanishing. So this makes sure that this quantity is vanishing, right? So this is, I just consider R to be infinity. But if you do the same thing, if you take a function derivative of these two terms, with respect to phi R, and evaluate at R to infinity, then this is not vanishing. The reason is easy to see. The W phi is equal to u phi minus m squared. So W phi itself is vanishing at R to go to infinity. However, if you take the derivative, then you get some u phi phi, the third derivative of u. And this is actually, in some model, is just one constant. Let's say you have a g phi to the cubic term, and then this is the constant. And then and in the end, you do not get the vanishing result. And because this term actually depends on L, so these two terms will give you some divergent result. Well, it's also cutoff dependent because so this is what we found. Now this
Sorry,
is
can you just make a comment before?
Yeah, please.
So I don't think this is true actually. You can just take the free propagator when like coincidence limit, and it's gonna be a finite number because we'll have to regularize it. So it's not actually gonna vanish even in the free theory.
You mean this term is not vanishing?
I mean the Green's function when the arguments are the same is not zero.
Oh, okay. So this is actually not the standard Green's function actually. So this Green's function actually depends on the Gelfand and Yaglu theory. So you have to be, I mean, when you solve the Green's function, you have to be careful with the boundary conditions. And in that case, I think we have paid a lot of attention to how to get this formula. I mean, so for example, let's us go back to this equation, and then here usually you have some in boundary conditions at let's say initial conditions. So at r equal to 0, then you give, let's say decide dr r equal to 0, maybe it's 0 or 1, I don't know. And this also will lead to the same boundary conditions for your Green's functions. And when you calculate the Green's functions, you really have to take all these boundary conditions into account. So yeah. So maybe if you compare the propagators so on and so forth in the KFT, maybe there's slightly difference. I'm not sure.
Yeah, I really have to take the boundary conditions into account, but usually when you do this, that's when you keep the R and R prime separate. If you take them the same, it doesn't necessarily have to vanish at infinity. Even for like a normal Green's function for a free case, it's also the same in the bounds presence. It doesn't necessarily have to be zero, even though the boundary conditions you impose it to be zero when R is not R prime.
Well, from this formula, if R equal to R prime, it's not necessary to be infinity. Just any constant Green's function should be zero, as you can see from here. Now, unless we made some mistake, but yeah. I mean, we could have made some mistake, but I mean, this is not just related to infinity. Any constant Green's function here is zero, right? This is
maybe we can discuss it later. Sorry.
Yeah. And then this is a summary of this section. So we show how to compute the functional derivative of a functional determinant efficiently. So you can use either the Dunning formula or PL formula. Then you need to compute several Green's functions for each L. Then we found that the functional derivative of the Dunning formula is actually divergent, and we think that actually this formula is valid all on shell. Then, but in our paper, we do use the BL formula and find everything's fine. We did check the cutoff independence numerically, and we get the quantum corrections. And since in the parameter, the benchmark parameter we choose, actually the quantum corrections is very small, so I'm not going to show you the numerical results. So this talk is more about how the procedure, what we do in the paper. After this part, then I will very briefly discuss how to compute the backreactions to the plasma. Well, this is really is kind of it's not finished part. It is really some mature source. So I will stop halfway basically. So again, let's back to the bubble nucleation at the finite temperature. As I said, actually, the bubble energy is not zero. The total energy, the field configurations. And so imagine you have let's say have a plasma. This is indicated by the red color. And so suddenly at some point you have a bubble nucleation here. So I picked in my understanding or just my naive from my naive intuition, actually, I can see that somehow the temperature in this region probably will decrease a little bit. Well, as we know, actually, energy is not necessarily conserved in canonical ensemble, right? This is how you define the temperature. Energy is not conserved. But still, I feel that there should be some backreaction effects. Maybe these backreaction effects are very small, but I can imagine that if the phase transition strength alpha becomes larger and larger, and then the vacuum energy part, the scalar field energy plays more and more important role, then probably the backreaction effects becomes important. I don't know. Now how to calculate the backreaction effects? The thing is that the bubble actually described by the 1-point function, right? Then the plasma or particles are described by 2-point functions. So we need to construct coupled equations of motion between 1 and 2-point functions. And can be perfectly done by the 2pi effect action. Now before I introduce you the 2pi effect action, I want to mention that the probability calculations of bubble nucleation at the finite temperature suffers many uncertainties. I mean, there are again many papers by Anders and also Oli. So here I will actually start with some prediction function, which can be actually an effective field theory, which is not necessarily the original theory. For example, this can be obtained by dimensional reduction, and then so you actually have three-dimensional theory. So this is why you have D3x, not D4. Okay. And it started with this non-local terms, J and K. K is non-local source. then your one-point function can be defined by the functional derivative of this partition function with J, and this is with these sources. Then again, you take a Lagrange transform, right? Then you can, well, so just a simple exercise, and then you can take functional derivative with to the one-point function, two-point function. Well, this two-point function is a connected two-point function. Then you get these equations. So in the absence of the external sources, then you get just the equation motions, which are what we want. Now the 2PI interaction has a general form. You have the class part, the class part of the effective set, and the functional determinant, and also have some two loop terms which can be represented by the 2PI Feynman diagrams. So start with this, actually you can derive the coupled equation motion for phi and that phi, and probably you can do some localization procedures. Then I think one finally can arrive at a coupled scalar equation motion and kind of Boltzmann equations for the well for the maybe particle distribution functions. Yeah, so I will just stop halfway and then I'll give my summary. Just check the time. Okay. So force vector decay can be formulated in terms of the 1PI fraction. And we show how efficiently compute self-consistent bonds and related quantum corrections to the decay rate using existing formula. And we, in our calculation, we found a dummy formula may be valid only on shell. I mean, this is at least what we observed. If you take functional derivative, it gives a divergent cutoff dependent result. Well, maybe it's, I mean, somebody of you maybe can have can give a check. We could have made some mistake at somewhere. And then 2PI action can be used for studying backreaction effects in bubble nucleation. And that's it. Thank you very much for your attention. I think, yeah, I can.
Thank you very much, Wen-yuan, for your nice talk. So are there any questions from the audience?
I would have another question, if I can.
Yeah, please go ahead.
Did you have a chance to check what's the influence of this derivative of the determinant on the nucleation rate in some model? Is it a visible effect or not?
Yeah, we didn't. So we actually, in our paper, we used the lambda 5 theory. I mean, means a G5 cubic term. Yeah, I mean, a very similar model. I mean, so our paper is kind of formalism oriented, or it's kind of theory. And we looked into the numeric result, and the quantum corrections is very small, are very, very small. So I didn't bother to really show you our numerical results. But I think maybe in some finite temperature phase transitions, there might be some situations where these corrections associated with the quantum corrections to the bonds could be important. I don't know. I didn't.
Okay, thanks.
No problem.
Okay, Ole, go for it.
I wanted to ask this, can you imagine a situation where the quantum corrections to the bounce are large, but the two-loop correction isn't? Yeah, what kind of circumstances might lead to that?
Okay. Actually, the quantum corrections to the bonds actually is in the conventional way is actually two-loop corrections. So if you by power counting, I would say imagine they are actually the same order. I mean, so we call it a one-loop effect action, but if you expand your effect action, 1PI effect action around the classic bonds, then you actually get some two-loop diagrams. So in the end, you are calculating some two-loop corrections to the decay rate, and also, I think.
I was thinking maybe like if you have some additional parameter like large N, something like that,
Yeah.
In which case you don't just have loop counting, but some sets of diagrams are enhanced compared to other sets of diagrams, not just based on loop counting. Yeah, if there's some situation there, maybe where these terms that you've computed are more important than, for example, the two-loop sunset diagram.
Yeah. Well, I think yes, because in the paper by Beyond Garbage and Peter Middleton, they somehow try to argue that as you said, they use a large n, introduce n copies of some fields, and try to say what they calculated could be important. I mean, so otherwise in these calculations you do not consider other higher two-loop corrections at all. So they try to justify the calculations using that kind of argument. So I can imagine such a situation actually.
Thanks.
Okay, thank you. Any more questions? Okay, then maybe I can ask one more. So this quantum correction to the bounds, how should I think about this physically? Because I guess like technically this is not a gauge invariant quantity, I would imagine, similar for like corrections to effective potential, for example.
Well, it's not necessarily have a gauge field in our case. I mean, you just consider the standard model by Coleman, and then so you have the scalar field, no gauge field. It's because this is everything zero temperature. First vector case probably. I mean, if you consider standard model, then gauge fields, gauge dependence, normalization, scale dependence, so on and so forth, everything comes. But in our case, we didn't really consider all this stuff.
Okay, thank you.
Yeah.
Okay, so unless there are any further questions, I guess we can thank Wen-yuan again.
Thank you very much.
Okay, so that's it for today's talk. And next month we will have Laura Battini. We'll talk about some tunneling in and hadronization. Okay, thank you, and see you in a month.
See you.
Thank you.
Thanks a lot, Wen-yuan.
Yeah. Take
Thanks. Bye.
Bye bye.